Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 2nd, 2026, just 6 days ago. It introduces a fully disaggregated serving system that reduces job completion time by up to 91% for complex multimodal models. The paper is titled vLLM-Omni, Fully Disaggregated Serving for Any-to-Any Multimodal Models. And as we'll see later, the efficiency gains for pipelines that handle text, audio, and video simultaneously are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. To understand why serving these models is hard, Figure 1 illustrates the typical any-to-any architecture. Instead of a single monolithic model, we have a pipeline starting on the left, with diverse inputs like text, audio, and video. These flow into modality encoders, such as Whisper or Vision transformers, which convert the raw data for the central autoregressive large language model. After the LLM processes this information, it directs modality generators, like the diffusion transformer in the green box, to synthesize the final outputs on the right. Well, Figure 2 breaks down 3 specific examples of these complex pipelines currently used in research. In panel A, we see the QN 2.5 Omni architecture, which splits execution into a thinker stage for reasoning and a talker stage that feeds a diffusion-based vocoder. Panel B shows a different approach with GLM image, chaining an autoregressive model directly to a diffusion decoder. Finally, panel C illustrates Bagel, which uses a mixture of experts design where understanding and generation are handled by specialized components. Alright, addressing those complex pipelines, Figure 3 presents the vLLM-Omni architecture. On the left, in panel A, the backend orchestrates the entire system using a disaggregated approach. This means each model stage runs on its own independent execution engine, which allows for precise resource allocation. Looking at panel B on the top right, we see the developer interface. Developers simply define a stage graph using modular templates for pre-processing and forward passes. Finally, panel C shows how end users can tune runtime parameters, like parallelism strategies, without ever needing to modify the underlying model code. So, Figure 3 gave us the tools. Now Figure 4 shows them in action with a concrete implementation of QN 2.5 Omni. On the left, the stage graph decomposes the model into 3 distinct nodes: a thinker, a talker, and a vocoder. The center columns detail the specific logic. For instance, the thinker stage runs a multimodal encode step before its main generation loop. Crucially, the yellow transfer functions manage data routing between these steps. This separation ensures that the compute-intensive purple forward functions can be batched and optimized independently for each stage. So, Figure 4 mapped out the logic. Now Figure 5 reveals the physical data transport. The left panel distinguishes intra-stage transfers, like passing the key-value cache, from inter-stage moves that route data between models, such as sending hidden states from the thinker to the talker. On the right, the diagram shows how the unified connector handles these flows. Each engine sends payloads via shared memory or the mooncake store, optimizing transfer speeds regardless of the hardware topology. Well, having established the transport mechanism, Figure 6 presents the end-to-end performance results. It compares vLLM-Omni in red against the transformer's baseline in blue, covering QN 2.5 Omni on the left and QN 3 Omni on the right. The top rows track latency, where lower is better. Notice the dramatic drop for QN 3 Omni with job completion times falling by over 90%. In contrast, the bottom rows measure throughput. Here, the red bars for tokens per second soar, confirming that disaggregation successfully eliminates the monolithic bottlenecks. Okay, Figure 6 proved the performance gains, so Table 1 investigates the potential cost, the data transfer latency between these disaggregated stages. It breaks down the time, in milliseconds, to move data from the thinker to the talker, and then to the vocoder. The results are striking because the overhead is negligible. Even using the distributed mooncake store, transfer times stay under 10 milliseconds. This confirms that splitting the model across GPUs introduces virtually no penalty compared to the total inference time. Wrapping up, 2 takeaways stand out. vLLM-Omni fundamentally changes how we serve complex multimodal models by treating them as flexible graphs rather than rigid blocks. This disaggregated approach slashes job completion times by over 90%, proving that modularity is essential for scaling the next generation of AI infrastructure. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.